bounce detector project introduction. This is Aditya Patel and Sharad. And Sharad is a big tennis fan, and I have played tennis for over 75% of my life. So both of us connect deeply with this particular domain of tennis, and we are pleased to actually be able to pursue this particular project. So detecting whether a ball is bouncing in a particular frame is of great importance because that information can later be used to make line calls decisions. But we focus on the ball bounce detection problem, and we divided that problem into two modules. First is given a video, detecting where the ball is there inside the video or whether there is a ball, tennis ball, in the frame. So that's the ball detection module, the first piece. And the second piece is using the outputs from model number one to detect whether the ball bounced or not, which is a yes or no. And Sharad will talk about the first piece, and yeah. So Sharad, all yours.
Thanks, Aditya. Coming to data collection, we downloaded 8 tennis match videos, 4 professional and 4 amateur, representing a variety of court surface conditions, camera angles, and lighting condition. We use the Python package YouTube DL for this. Next, we extracted around 50,000 images from the 4 professional and 4 amateur videos each using OpenCV frame extraction. We then chose 126 frames from each of the 8 videos, ensuring a ratio of 1:2 for frames where the ball is in the front court versus the back court. We kept more frames at the back court to ensure that the object detection model has substantial data to train for the ball when it is much smaller at the back end of the court. 126 frames for 8 videos gives us 1008 original images. We also labeled the bounding box of the tennis ball in each image using a labeling tool called label img. So let me show how it looks like. So here's the tool, and these are the various bounding boxes for the tennis balls that are there. Next, we also reduce the image set proportionately to 504 and 256 to check whether smaller image sets would work as well as the larger image set. Next, we augmented the images using the Python package augmentation, which resulted in a augmented plus original image set of 887 images, 1764 images, and 3525 images. Next, we implemented object detection in YOLO V4 Tiny as it is a faster model and also because there is a controversy regarding YOLO V5. YOLO V4 uses a C and CUDA based framework called Darknet. We use pre-trained weights and then custom train on the label image set that we discussed earlier. As we increase the image set, the performance metrics of mean average precision at 0.5 increased till 70.1. Let me show you that. And however, the performance of the model at the back end of the code was not that great. Let me show you that video. So you can see here that the ball is not being detected that well at the back end of the code. And that is why we increased the network resolution from default 416 to 1664. So this increased the training time, but it also improved the ball detection at the far end of the court. Let me show you that. Yeah, as you can see, the ball is being detected at the far end side of the court. And this also actually led to a very high map value of 93.9%. And as you can see here, we actually had to early stop the training, otherwise the model would have overfit. So this YOLO V4 tiny model trained on 3525 images and on a network resolution of 1664 is our chosen object detection model to be used in subsequent steps. Over to Adi for the next component.
Module. Now, if we forget about data science, if we just think about how a human being makes a decision on whether a ball bounced in a particular image or not. Like, let's say if we give a photograph of a tennis ball in a tennis court and ask somebody to tell us whether it seems like the ball is hitting the ground or not. Now, it would be nearly impossible for the person to say that with any kind of confidence, because in order to decipher a ball bounce, the human being would need to review, let's say, 5 images in the past from which tell him or her where is the ball coming from, and 5 images in the future, like where is the ball going. And so based on that information, the human can tell whether the ball bounced in the middle of that particular window or it did not. And so just based on a single frame, it is nearly impossible to make such a decision. So we use an so in when trying to translate this tennis domain problem, into a data science problem, we bring in the exact same intuition. We convert our data set into windows and we model this as a many to one sequence prediction problem. S- just for that simple reason that just like a human being cannot take a decision based on only a single frame showing a tennis ball hitting or not hitting the ground, the human needs to review frames before and after that particular event. And so that's what our pipeline is all about. We translate the output from model number one, which is a text file for each particular image. We process those thousands of text files, extract the ball coordinates into a single CSV file, and very importantly, we create windows. And that's a big step. And we spent a lot of time thinking about how to actually model this tennis domain problem into a data science problem. And eventually, like I mentioned, we decided to mimic how a human being would take such a decision, and that would be based on a trajectory, which shows what has happened in the past, where the ball came from, and where the ball is going. And that information and those features go inside a sequence model, and the output is a one or zero. Like in that particular window, was the ball bounce detection event? Did that event happen or not? Okay, and so basically, we tried out a wide variety of architectures, sequence models, and we achieved an AUC of 86% on our test set using an LSTM architecture. We explored many others as well, but this we are reporting on the ones which work the best. And for a window size of 10, so these are 10 sequential consecutive frames. If you look at the top left here, we see that for this particular window size, the training progresses very smoothly, and the gradient descent works very well, starting from epoch 0 all the way as we increase the epochs. And so that was pretty encouraging to see. And like I mentioned, we achieved 86% AUC on the validation set. And one thing I would like to mention is that we use the metric AUC primarily because of the imbalance in the data set. Now, in general, in any tennis match, the ball is not bouncing, like the ball is in air in more frames than the ball is hitting the ground. And so, assessing how the our classifier is able to distinguish between positive and negative classes in such an environment, we chose this particular metric, and we are pleased to report our results here. Thank you very much.